So this video covers statistical hypothesis testing. I'm putting the hypothesis here in quotation marks because we already mentioned that this is not really a hypothesis and definitely not a scientific hypothesis. Nevertheless, we should go over it. We'll talk about what type 1 and type 2 errors are. And there is actually one benefit from this. So one thing we can derive from statistical hypothesis testing that's actually relevant is statistical statements that you can't make. So there are some statements that are not allowed, and we haven't covered that yet. So that makes this section worthwhile. But otherwise, as far as I'm concerned, you can forget about statistical hypothesis testing after this video. So there's a conspicuous lack of a star here. In my opinion, this is not an important concept. So in the previous video, we already identified that it's a pitfall, statistical hypothesis testing. So it sounds like you're doing something important, but you're really not. So this is no guarantee that any of this has scientific value. In fact, a statistical hypothesis is not even a hypothesis. So we look this up here. A hypothesis is a proposed explanation for a phenomenon. So what we consider a statistical hypothesis is just an expectation or a conjecture. So we say there is no difference, or we say there is a difference as an alternative hypothesis. These are just conjectures or expectations. This has nothing to do with an actual hypothesis that can be tested and that can provide scientific insight. I'm really at a loss why this is called hypothesis. And, Fisher was actually not such a savory person as a whole. Maybe this was just a marketing move, He figured, well, let's call this hypothesis, and everybody thinks they're doing good science. And, if that was his intention, it was certainly a roaring success. So in some way, this wrong terminology has really caused massive damage. And I've given you some papers that's not just my opinion, that's a really well-recognized problem. So don't put statistical hypothesis in your theses or in your report at the end of your introductions, where you would usually say, hey, this is what I'm going to try to test, or this is what I try to figure out. Those should be actually explanations for something, not expectations or conjectures. Okay, so with that out of the way, we can still do statistical hypothesis testing. And even if I accept that it's not a scientific hypothesis, even then it rarely has any value, because for most tests I know a priori that the null hypothesis is false. So if I say mean A is the same as mean B, I most of the time, with very few exceptions, I concede that there are exceptions, but in 99% of scientific studies I know that this hypothesis is false, and then this test is really pointless. So stick with what you learned so far. You make a valid statistical statement and you convey how certain you are that you are right about that. And that usually involves a magnitude that involves an effect size or a difference being a certain size. This really is not an important piece of statistics. But in any case, so let's go through the motions. And I promise you there'll be something interesting at the end in any case. So it goes like this. If I have two means, for example, we can use our t-test example from the previous video. So we have a variety A with a certain yield per hectare and another yield with a different. My null hypothesis, so my conjecture, is that the true mean of A is the same as the true mean of B. Or I could also actually state this slightly differently. Is random chance a plausible explanation for the observed difference? So is the difference that I observed just a random artifact? And you already know that is the p-value. So if I formulate it like this, then it's at least an actual hypothesis. So it is an explanation. So random chance would be my explanation for the observed difference. But I've never seen anyone state the null hypothesis that way. They should. Okay, so and the answer to that question is always yes. So if I get a p-value of 0.2, I say yes. I would get a difference as big or bigger 1 out of 5 times just by random chance alone. And if my p-value is 0.05, again it's yes. So that would happen 1 out of 20 times. P-value of 0.001, 1 out of 1,000 times this would happen. And at some point, I would reject the null hypothesis, right? It just becomes too unlikely. So then I accept that there is a difference. So I accept the alternative hypothesis. And if I reject the null hypothesis when it's actually true, then I'm making a type 1 error. So the probability of making a type 1 error is actually p. So that happens 1 out of 1,000 times, right? So I'd be wrong. And the type 2 error is the opposite. So I accept H0 when it's actually false. But that is actually also something that you wouldn't actually do. And that's also recognized. So that's our pitfall number 2. That's an error that you should never make. So you never conclude that H0 is true. So if your p-value is large, it doesn't mean that there is no difference. So it's actually not considered to be an error. So they call it type 1 error, but that's another way that the name was chosen inappropriately. So everybody understands this is not an error. So what you really do is you don't fall into that pitfall. You simply say there's not enough data to reject the null hypothesis. So the reasoning behind all this is actually totally sound, and I can illustrate this with a useful analogy. So imagine that we're flipping coins. So you're betting for something, and your partner is flipping the coins, and you may have heard of trick coins. So instead of having a head and a tail, so 2 different sides, a trick coin would have 2 heads or 2 tails. So for the purpose of illustration, how statistical reasoning works, just assume my null hypothesis is that's a normal coin that my partner is flipping there, and the alternative hypothesis is that this is a trick coin. And we can now proceed and collect some data. And let's say your opposite throws the coin 3 times, and he or she wins 3 times in a row, right? So head, head, head. Would you get suspicious that might be a trick coin? And most people would probably not get particularly suspicious. So the first throw is, could have gone either way, so we haven't established a pattern. The second coin, so the probability to get 2 heads in a row then, after the first coin was thrown, is 50%, right? And then the third one would be still multiplied by 50%. That would give me a total probability of a quarter. And most people would still say, well, that happens 1 out of 4 times, so there really is no evidence to reject the null hypothesis that this is a normal coin. This can surely happen, And the other interesting thing to note is that this does not allow any inferences on the probability that this is a normal coin. So a high p-value does not mean that the null hypothesis is true. So it could very well be a trick coin, right? We just don't know yet. We need more data. So that's exactly how statistical reasoning works too. So when would you become suspicious? 4? 5? So let's see what the probabilities are. They're easy to calculate. I just keep multiplying by 0.5. Most people would get suspicious at 5 or 6 throws in a row. That seems like odd. The chances are 1 in 100 here. I would want to see the other side at this point. And as we go on, at some point you would certainly reject that null hypothesis. Now, let's imagine you get the offer to turn around the coin. But if you're wrong, then you have to pay. So something is at stake now. Let's say you have to pay $100, $1,000, or $10,000. When would you turn over that coin? Or when would you have enough evidence to reject the null hypothesis? And you notice, as the stakes are getting higher, my alpha level will get increased. So I won't reject the null hypothesis if something is at stake, right? So again, that's the same idea when you do regular statistics. I might want to turn over the coin if there's nothing at stake, if I have the freedom to turn the coin anytime I want. I would look at it after 3 or 4 throws already. But if there is something at stake, so if there's a price to pay if you get it wrong, then your alpha level would increase. And then my last question is, can you ever be 100% sure that H0 is false if you're just collecting data like this? So without turning the coin over, so that would be sort of equivalent to measuring all 10 billion trees of my population, could you ever prove that H0 is false? And obviously you can't, right? So there will always be a small chance that I get a lot of heads in a row without that being a trick coin. So it will be a small probability, but it's possible. So I never can conclusively prove that H0 is false or that there is no effect. And I used the court analogy before also to illustrate statistics, and it works also here. So if there's not enough evidence for a conviction, does that prove that the accused is innocent? No, it doesn't, right? So that logic does not compute, even though people want it to be true. If somebody gets a not guilty verdict, they want everybody to believe that this is proof that they are innocent. Really is not, right? So it's a matter of whether there was actually enough evidence presented for the judge to make a conviction. And also, can you ultimately prove guilt? No, you can't. So it's just as with a p-value. You can only prove beyond reasonable doubt, and the doubt is a very small p-value, that that person is guilty. So those are the only tools we have in statistics, and it doesn't go beyond that. So this is it's limiting, and it doesn't sit well with us that we can't prove innocence or that we can't prove no effects. But it is what it is, so we have to live with those limitations. So to sum this up for what it means for our statistical statements, I can only assess if I'm right or wrong about my alternative hypothesis, not about the null hypothesis. So I can say I'm 95% sure that the true mean is larger or smaller some value, but I can't do the same assessment for the null hypothesis. So the p-values are always a metric whether I'm right or wrong about the alternative hypothesis.